fast.
Well, I know you can be, yeah.
Mr. Cooper has no, like, he just wants
That's what people don't.
Friday? Friday?
I think here in the South, though.
Friday? He was just off to the
All right, guys. Everybody with me?
Yes.
Guys, okay, so we're kind of shifting gears and we're starting related rates today. Now, related rates, when I was in college, was a huge topic. And it used to be back in the 70s and 80s, early 90s, it was a huge topic in calculus. It's still a topic. It will still show up. It's just you're rarely going to see a 9-point free response question on that. So to me, when I think about a 108-point test, when you have 6 9-point free response questions, that's what's driving your material. So because we don't see this at the same rate, no pun intended, as we used to, we are going to still look at it. We're going to still examine it. But I can tell you on your AP test, the problems that show up on related rates tend to be mild in comparison to what we will do in here. But we will cover it pretty thoroughly in here because if you ever take it in college, they cover it pretty thoroughly in college. And if you're looking at your assignment sheet, our test is on the 16th. So today is Monday. We're going to do this Monday, Tuesday. Of course, we're off on Wednesday. Yes, and then we're going to come back and do it Thursday, Friday. So we're going to have 4 days of related rates. And like optimization, these problems have the same kind of mentality to them, even though it's going to seem much different. It's not like optimization where literally you are robotically, once you get that equation, you are kind of robotically going through the process. Not the case for related rates, but it is the same kind of mentality in what you need to do. Are y'all with me? Okay, now you know that when you take a derivative of something, what are you essentially finding? Slopes, which are rates of change. And what we've been typically doing is finding, before just a couple of days ago, we were always working with explicit equations like y equals, right? So when we took a derivative, it was always a dy dx. So we were always finding the rate at which y changed, dy, with respect to x. What we're going to be doing a ton in this chapter is finding how rates change with respect to time. So we're not going to be dy dxing or dx dxing. We're going to be dy dting or dx dt, or even better, we're going to be looking at equations that you know about, like area of a circle. Area equals pi r squared. And when we take the derivative with respect to t, we will have an equation that shows how area is changing over time with respect to the radius over time. And we will have those related. We will see how those rates are related. And if we have something that involves more than one equation, like volume of a cylinder, which is pi r squared times the height, that volume equals pi r squared h. If I take the derivative of that, I will have a rate at which volume changes with respect to the radius's rate and the height's rate. And you can look at how all of these are changing. And then it's even better than that. Well, it's even better. Also, like if one of them is not growing, like if I say, well, what if volume is changing on this cylinder, but I keep the radius constant? Well, we'll talk about how to actually fix the radius so that it's not changing and just let the height change. Or fix the height and let the radius change. And again, all of these things are going to be related because it's going to be a new equation that talks about these different rates. All right? So again, you have to kind of lock in your brain that if you're taking a derivative with respect to time, it's not a ddx anymore. It's a ddt. So you know how when you were taking derivatives just last week, and you took a derivative of like x cubed, and you got 3x squared, and you didn't bother writing the dx dx because it canceled? Well, you can't just do that anymore. If you're taking a derivative of an x cubed, you're going to get a 3x squared dx dt if you're taking it with respect to time. And if there's a time variable in there, then you would have a dt dt, which might cancel. So the same rules apply, but just stick to it. Kind of follow these. I've got some guidelines for solving them. And you're going to have to read word problems kind of carefully. And then there's a couple strategies that I'm going to offer you that I think are helpful. And they're not always the best way to do it, but they're usually the best way to go about this. And you'll see that as you go. So we're on page, what, 40? 7. Okay, so related rates, I just started off with the volume equation, and I wanted to show you that if you were taking a derivative of, say, I'm just picking this just to kind of show you the process. The derivative of a volume equation with respect to time. So maybe this is a just some volume of some object, and I want to see how the radius and the height are changing as the volume changes, or how that possibly could be related. I can ddt both sides. Now when I ddt v, I get 1 ddt. Kind of like when I ddxy, I got 1 dy dx. Are y'all with me on that? But when I go to the other side of the equation, there are 2 variables. Now one strategy I did not employ here, but I will, if there's any way, and we kind of did this with optimization. Do you remember with optimization, before I took the derivative, if I had 2 variables over there, I knew that if I took the derivative right there, it would get kind of messy. So I liked to get everything on one side in terms of that one variable. Well, we're going to do that a lot too. Like for instance, if there's some relationship between height and radius that I know, and I can make a substitution right now and replace that h with something that has an r in it, well, it's going to make my life a little bit easier when it comes to actually doing this problem. That way I won't have to take the derivative of 2 separate equations, and we'll talk about that. But for this example, I didn't do that. So you have to be able to look over here and see if there's 2 variables that are different, or even if they're the same but they're separated like a product or a quotient, you go and pull out your derivative rules. So I'm going to group that pi over 3 with that, and here's your product rule. First, d second, and the derivative of h is dh dt, technically 1 dh dt. And then plus second, and then the derivative of the first is 2 times that ugly thing, 2 pi over 3, r to the first, and then again, dr dt. So you have a new equation that relates the rate of change in the volume to the rate of change in the height and the rate of change in the radius. Are y'all seeing that? So it shows how all they're related, the relationship together. Now you also end up having the actual height in there and the actual radius in there a couple of times. And you'll notice I don't have the volume in there because when I took the derivative of the volume, the derivative of v just became 1. So sometimes you're still going to have to know the actual values at a particular time. Like they'll say, hey, and by the way, do you know that like, you might have experienced this, but like if you have a big thing of iced tea or water or whatever, and you have, you know, the little containers that have a little spigot on it, and you push it in there, and if it's full, the water is what? It's coming out really fast, but as it gets way down, you're just getting drips, right? So the rate of change over time was changing. So sometimes what they'll ask you is, hey, talk to me about the rate at which the volume is changing at a certain time. Well, that might be the rate at which the volume is changing at a particular time, or they might say when the radius is 4, or when the height is 10, because you know that the height in that container of water, or whatever it is, the higher the height, the faster the volume is changing, right? Because it's leaving faster. The lower the height, the lower the volume is changing. So the actual height and radius might be important to the problem. So you're going to have to learn to read equations and pull this information out of there. And I'm going to practice that with you a number of times today. And again, if you're doing all these problems in class, when you're with me, if you are doing these problems at homework, you shouldn't see anything really surprising on your test. But when you start skipping those homework problems, again, you might be good enough, a lot of people are, to go and see a problem you've never seen before, and you might be fine. But you guys saw that on that last test. If you had not seen a problem, and I was pretty kind to you on that last test, by the way. But if you hadn't seen a problem before, first time you see it, it's kind of a coin toss sometimes whether you can get those equations. So be careful out of that, but that's the idea. You are using what you know now about implicit differentiation, right, to take a derivative, but the new thing is we're taking the derivative with respect to a different variable. Now, had there been a t in there, like right here, if this h had been a t for whatever reason, then first d second, what's the derivative of t with respect to t? You wouldn't have bothered writing that, right? So just like a dx that you wouldn't need, a dt, 1 dt would just cancel. But most of the time, we're not going to have time in these equations. We're going to have other variables that are changing with respect to that time. Are y'all with me? Okay, so some guidelines. When you're reading these problems, and this is ultra important because sometimes I'm going to give you points for just writing down stuff that you've pulled out of an equation. And if you don't write it down and it ends up showing up correctly in your equation, that's fine to me. But if you do write it down and you get a wrong equation, you might still get points for identifying certain values. So identify every quantity, the stuff that you have to determine, like if I'm looking for what is the height when the blah, 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 blah. Make sure you say h equals question mark or whatever to point out that you understand what's going on. If I'm saying, hey, determine the rate at which the height's changing, the rate at which the height is changing. What did I just ask for? The rate at which the height is changing. That would be a what? A dh dt? So if I said, what is the height? You'd say h equals. If I said, what is the rate at which the height's changing? That would be a dh dt equals. So we have to make sure we're identifying, read slowly. Sometimes it's obvious, sometimes it's not quite as obvious, but you have to learn through experience and through practice what these things are saying. And then if it's possible to make a sketch, sometimes that is really helpful. Sometimes I'll give you a picture to save you the trouble, especially maybe early on. But definitely do that before you get started, because that's the key to really identifying what you're trying to do and then filling in stuff later. It says write an equation for the amounts that are involved. Like if I'm calculating the rate at which volume is changing, I need to probably start with what kind of equation? A volume equation. If I'm talking about the rate at which area is changing, I'm probably going to need an area equation. And it's important that you identify that, because it kind of like I had somebody on the last test, I asked you about, I want to say it was area of a fenced in thing, and somebody did perimeter and took the derivative of the perimeter, which they did all their work correctly, but I didn't want to find anything about perimeter. I was trying to find stuff about area, or vice versa, I forget. But anyway, make sure that you're reading and writing down this stuff before you kind of get started. Third thing, make sure you're given enough of the rates. What I mean by that is, right here, what if I'm trying to solve, and remember, here's my volume equation. Volume equals pi over 3 r squared h, right? So when I took the derivative of the pi over 3 r squared h, I ended up with this. Well, if I ask you to find the rate of change at which volume is changing, the rate of change, you're going to have to know both of those other rates, aren't you? And if I don't know both those other rates, that's a problem. And I can show you how to figure that out. What I like to do is if I write down all my information, and I'm like, all right, I'm looking for the rate at which volume is changing, but I don't know this, then I'm going to read carefully through the problem and see if there's some kind of a relationship between dr and dh. Like maybe they tell me something like, hey, the height is 3 times the radius. Well, if that's the case, I could solve for r, right? Plug that in for r right here. Simplify it. Which ends up being pi over 9 h cubed. And now if I took the derivative, guess what's not going to be in my equation? dr dt. Are you following me? So if I don't have one of these rates, one nice thing to do is make a substitution initially so that will never show up. See, now when I take the derivative of volume, I don't have a product rule with an r in there. All I end up with is 3 times that h squared dh dt. And the dr dt never comes into play. Now that's my strategy. Now a lot of textbooks will say, oh, you don't need to do that. You can just come in here and take the derivative. You can come in here and say the derivative of that is dh dt, and the derivative of that is 3 dr dt. And then now you can solve for dr dt, because in this case, what would dr dt be equal to? Couldn't you multiply both sides by a third? Yes, no? So now, even though I don't know dr dt's value, I could replace that with this. So some people like doing it with two separate equations, taking the derivative twice. But I have found that my students tend to do better across the board when they make those substitutions early and get what they don't have out of the way. But you're going to have to make a choice. Normally, my students that are very, very strong don't have a problem with taking the derivatives of two equations and making substitutions. But the ones that tend to like, all right, I'm a good student, but I struggle sometimes, and sometimes I get lost in the math, they, across the board, tend to do better making substitutions and getting rid of variables that I don't have rates for. So anyway, that's something that we'll talk about all the way through these problems. And that's what I mean when I say make sure you're given enough of the rates so that when you implicitly differentiate, you'll be able to solve for the missing amounts. Okay? It says, I say you should be able to make a substitution before you differentiate. This is what I'm talking about. And that will eliminate one of those variables. And I've also found if you eliminate a variable, the differentiation tends to be easier. Because a lot of times you don't have the product rule anymore, right? Like we just saw, once the R went away, I could put those H's together. It was just a simple power rule. So sometimes the math ends up being easy. Now I can tell you, there's one example off the top of my head where the math does not end up being easier. So I'm just telling you, as a whole, I think you're going to be better off making substitutions before you begin to differentiate. All right? Number 4, implicitly differentiate. That's the chain rule, essentially, or the power rule, or whatever it is that's going on. And make sure you do that with respect to time, which is almost entirely what we're doing on this section. And then when you're finally done, substitute every known value, all the stuff that you wrote down from the beginning, plug it all in there, and for the rates, the values, anything you have, plug it in there and solve for the missing amount. And that's related rates. So there's the process, and you're going to see it, the process doesn't really change. You're doing all of these things. It is easy to get lost in these problems from time to time. So practice makes better for sure, and I would encourage you to not skip on these homework problems. At the very end, I'm not even going to say just find an equation, because the practice of implicitly differentiating is very new to you guys. You're going to probably need to practice. All right? So, verbal statements. Let me just give you some practice on these. I say water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. So what am I talking about when I say water is coming in at 10 cubic meters? What value? Of what? How do I quantify that? It'd be a volume. Now another hint is the units, cubic meters. Okay? But water comes in, it's a volume of water. It's not a length of water, right? It's not an area of water. It's a volume of water. So that's a cue to you to go, okay, it told me that the rate was 10 cubic meters. So dV dt is 10 meters cubed per hour. All right? And I also know that V stands for the volume of water that's in the pool. So those are units. If you read that, you would need to be able to pull that out of that expression. How about this? Determine the rate at which the volume of the pool is increasing after 3 minutes. That really means at 3 minutes. Okay? So the rate at which volume is increasing would be what? dV, the rate at which volume is dV dt is, I don't know. That's what I'm looking for. So you would want to write, that's the volume. And again, they asked for a specific volume. Kind of like the water in that container. It's going to change a whole lot more quickly at the beginning because there's just so much more pressure on the water pushing it out. And as it gets lower and lower and lower, it's going to slow down the actual volume that's changing. So I want to know the rate of change of the volume at 3 minutes. I'm going to write that down. Right here, when the radius is growing to a length of 4, what is that? That's just the R equals 4. I didn't say the rate of the radius is growing at something. That's just R equals 4. At what rate is the area of the surface of disturbed water changing? dA dt. Area, the rate at which the area is changing. dA dt, and I don't know it. I'm looking for that. What is the rate of change in Buss velocity? We haven't done a lot with velocity and acceleration and that kind of stuff. If you've taken physics, you've done a little bit of that, and that's going to be maybe helpful from time to time, but honestly, don't make it too helpful. it'll be very helpful when we do position, velocity, acceleration, but just kind of stick to what you know here. So the rate at which Biff is velocity changing, it says what is. So what is dv dt? When the rate of change in his position, so most of the time we're talking about a position change, we think of x, but you could use p, I guess. dp dt or dx dt is 12. Are you seeing that? And then finally, if the distance is s, if the distance s is decreasing at a rate of 400 miles per hour, so if increasing is positive, then decreasing must be negative. So I would say, if distance is s, I would say ds dt, that's the rate, equals negative 400 miles per hour. So those are just examples of phrases that you might see in a word problem. But anyway, as we jump into these, try to employ these practices and see what we can do. And a picture always, not always, is often helpful. Okay, so let's check out the ladder problem. All right, so the ladder problem says a ladder 25 feet, and I think it's going to be helpful for you to draw a decent picture. It says a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So slowly pulling it apart, 2 feet a second, 2 feet a second, 2 feet a second. Now what do you think's happening as I pull that rate at a constant rate of 2 feet a second? Is the length of the ladder changing? No. What's happening to that ladder at the very top?
Its position on the wall is changing.
So as I'm pulling it like this, look, it's slowly coming down, and then what? It really is going to end up speeding up as it gets towards the bottom, right? And then eventually just almost fall. Okay? So I'm looking at this, I'm going to draw a picture and say, all right, if I've got a ladder, let's just say is 25 feet long, right? It's leaning up against the wall. The base is pulled away. So as I pull away, what do you want to call this side right here?
X.
Call that X. What do you want to call this side? Y. So it says, that's X, that's Y. It says the base of this is pulled away at a rate of 2 feet per second. So what did I just give you?
Dx dt.
The rate of change of X, dx dt, would be 2. And is that increasing or decreasing? So it's positive. Now, then it says, and I got everything labeled, how fast is the top moving down? So what's changing when the top moves down? And the question was, how fast, right? So dy dt is what? Question mark, but it asked for a specific dy dt. It says, how fast is the top moving down? So how fast is the y changing when? When the base is 7. So I want to know how fast that is when x is 7. Are you with me? Now, do I have a relationship that relates all three of these values?
Yeah.
I do, which is the Pythagorean theorem. Now, sometimes the question will ask you things like, hey, at what rate is the angle of the ladder with the wall changing? So if I throw an angle in there, then I'm probably going to have to think more than just Pythagorean theorem because I need to work a theta in there. How do I work a theta in there? Maybe a trig function, right? And maybe, although I could maybe think if it's a 90-degree angle, even better than law of sines would be just a regular trig function, so you don't have 2 trig functions in there, right? So, but anyway, that's for another story. So right here, I want to find a relationship between these, and you said Pythagorean theorem? Okay, so I'm going to say, all right, let's check out x squared plus y squared equals 25. Now, here's why I want you to think ahead of time. Right now, if I take a derivative of this, what's going to end up in my answer? And I'm going to do this so you'll see it.
dy dt and dx dt.
I'm going to have a dy dt and an x dt. Now, I'm looking for the dy dt. I know the dx dt. I think I'm going to be okay. Yes?
Why wouldn't it be 25 squared?
Well, the units are squared. I mean, I can
but
put
it doesn't
25
like
units.
anything.
Oh,
It's
no,
really
no,
big
no, absolutely, yes, sorry.
Okay.
Pythagorean theorem, yes, sorry. My bad.
I
Are you with me?
I know.
But the units are also squared. Okay, so right here, let's go ahead and start taking the derivative. But again, if I had an extra variable in there, like a z or whatever, and I'm like, crud, I only have one rate, I'm missing two rates, then there's going to have to be another equation to help me link that extra variable to this. And my thought is, if there is, why don't we make a substitution ahead of time, and then we don't have to worry about it. Usually it makes the algebra better. So help me out with the derivative. What is the derivative of this with respect to time? So d dt, both sides. What do you get here?
2x dx dt.
So 2x dx dt. Now there's that first example of, normally we're used to taking a derivative with respect to x and we would just say 2x. But the derivative with respect to t is 2x dx dt, because there is no dx dx that went away. And then plus,
Mr. Curry, if you know that x is 7, why wouldn't you just go ahead and plug 7 in?
because, great question. She said, if I know x is 7, why wouldn't I plug in there? I am allowed to plug in values that don't change. So technically, 25 would be x squared plus y squared equals r squared, right? Or h squared if it's the hypotenuse. But I can plug the 25 in there because it is not going to change. It is a fixed length. But this length is changing. And this length is going to be changing. So if in your relationship you see something that is changing, do not plug a value in before you take the derivative. And if you see something that is changing, definitely plug it in. So like my original equation here might have been this. It might have been, I'll call it h for hypotenuse. Technically, it's h squared plus y squared equals h squared, right? But because that was never going to change length, it was fixed. And that's an important topic that she just brought up. Because I know that the ladder is always 25 in length, I am going to plug that in there. But by doing that, what do you end up getting? Check out the math, 2y dy dt. What do you end up getting here? 0, because there is no change in rate of the h, right? But if I were to plug a 7 in there right now, when I took the derivative of it, I would get no rate of change in x.
Is that when you lock in variables?
Sorry?
You talked earlier about like locking in different aspects to find whatever you're looking for. Like you use the example of the cylinder. If you want to see how like just the radius changing affects something.
I was talking about at times, sometimes the height might be fixed or the radius might be fixed. So in those cases, if they're fixed, which the hypotenuse is, plug that in, and then you will see how the other two sides are changing with respect to a fixed side here. Y'all seeing that? Now, again, if I didn't know that and I said, hey, this triangle is changing, blah, 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 and I just took a derivative over here, I would have a 2h dh dt as well. But because the hypotenuse isn't changing, I certainly know that the rate of change is 0. And look, there it is. You with me? So great question, even better than you think. Okay, now when it comes to solving here, I'm going to plug in what I know. I know that that is 2, so I'm going to come in there for dx dt, and I'm going to plug a 2 in. I already have a 2 there, and I know that x is 7, so I'm going to plug that in there. I do not know y at the second, and I am looking for dy dt. Now wait a minute. I don't know why, they didn't give it to me, but let's stop and think for a second. When x is 7, do I know what y is? And what is it? Y'all remember that Pythagorean triple? 24? Now that's, if you don't remember that triple, then you would have to go, okay, wait a minute. When the hypotenuse is 25 and the x is 7, the y can be found by taking 625 and subtracting 49, and that gives you what? 576, and when you square root both sides, you get 24. Technically plus or minus, but we know that it's a positive line. So I'm going to plug positive 24 in there. And then you can see I can solve for dy dt. So I'm going to take this 28, subtract it to the other side, make it a negative 28. I'm going to divide then by that 48. and this tells me the rate at which y is changing at this moment is negative 28 over 48, which is what, negative 7.
Do you have to simplify if it's 18?
On a multiple choice, that it would be there, but if it was a free response, no, they really wouldn't care. But then here's what's really important, your units. And the units are a lot easier than you might think, because literally they are giving them to you. They're saying change in y over change in time. And y is measured in what? Feet, and time is measured in seconds. So feet over seconds. And usually the units would matter. And so that would probably be a point. So if you're asking me off the top of my head, how would they give you points for this? They'd probably give you a point for making that statement. They're going to give you a point for having the right general equation relating this stuff. Sorry, I have it right here. I'll give you a point for right there, what's in the black right there. They're going to give you a point for the derivative, and then they're going to give you a point for plugging in those values, and then a point for your answer. So you might be looking at actually that's going to show over there, maybe 1, 2, 3, 4, 5 points, maybe a point for the units, especially if the units are abnormal and not just totally obvious. Maybe not totally obvious, but if they're telling you dx dt is 2 feet per second, it's pretty likely that that's feet per second also. Are you seeing this? Not too bad? Okay, let's check out the part B. Part B says, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing. All right, so let's go back to this problem. Let's forget all this Pythagorean theorem junk. I still have the same given information. So I want to find what? Not the rate at which that's changing, but the rate at which what? At which area of the triangle. So I'm looking for d area dt. That's what I want to know, but still when x is 7. So, same picture, same ladder, but what do you know about area? Okay, so area is 1/2 BH. Anybody got any ideas on area? And in this case, BH would be what? 1/2 x y. Since you like, y'all name them x and y, whatever you name them. Okay? And by the way, remember on optimization I told you I really like x's? So I tried to write things in terms of x. We don't care anymore, because we know how to implicitly differentiate. The only reason I told you I liked x's is because you were more comfortable with taking derivatives of x's. But now we don't care. You can call them h, y, b, type, whatever you want. As long as you're consistent, you're going to be okay. All right, so right here, anybody got any ideas for what to do with this 1/2 xy? Take the derivative? Okay, so if I took the derivative and I ddt both sides, what am I going to have to do to take the derivative here? And by the way, do I have, when you take the derivative of this, you're going to end up with a dA dt, which is what I'm looking for. If there's a variable in there, you're going to have a dx dt, which I know, but you're also going to have a what? A dy dt. Do you have that? Technically you do, because you just found it in the problem before. But if you didn't find it in the problem before, that's a problem. So do you have a way to relate x and y so maybe I could get rid of y? The Pythagorean theorem. See what I'm talking about? So like if you look up here and you're like, crap, I'm looking for that, that's fine. I'm going to have a dx dt, that's fine. But crud, I'm going to have a dy dt. Now, I can always just borrow it from problem number 1 because I literally found the dy dt when x is 7. I know that. But in this case, if I didn't have that, I could say, wait, I do know that x squared plus y squared equals 625. We had that from before, right? 25 squared. So if I wanted to, I could solve for y, subtract that x squared and square root, make that substitution, I don't have y anymore. So now when I take the derivative, do I have to worry about having a dy dt? So this is my advice to you, and I'm going to go ahead and solve it from here. But if you wanted to, you could have done it with the y in there and done a product rule. You're still going to have to do a product rule. But if I had done that, keep in mind, you would have needed to know that, and I would have to do that problem separately. Are you seeing that? And to me, rather than doing everything that we just did on the board before this problem, I'd rather make a substitution and not have to do that. Because on my test, I'm not going to snowball answers like that, to where one's going to affect your other one. I seriously doubt I'm going to do it. So how would I now, rather than do this, since I've made a substitution, how do I ddt this thing? Anybody? Obviously, the ADT there, and then what? Product rule. But at least this time when I do the product rule, I won't have a y in there. So how do you want to do it?
So, 1/2.
Put the 1/2 with the x. So first, d second. Now how do you take a derivative of that jump?
Double the bottom.
Double it on the bottom. So this x, this 1/2 x, the x is really up top. So 1/2 x times double that on the bottom. What's the derivative of the inside part? Be careful. Nope. Negative 2x. Be careful. Negative 2x what? dx dt. First d second plus second dy, or whatever, I'm sorry, plus second d first. What's the derivative of the first? 1/2 dx dt. So you're going to end up having to do the product rule anyway, but this time I'm free from having the dy dt in there to worry about. So can we plug everything in there that we need?
Yep.
So here we go. So dA dt would be 1/2 times the x value, and we know the x value is 7, and then times 2 square root of 625 minus 49, and then on the top, negative 2 times 7 times, what's dx dt? Another 2 plus the square root of 625 minus 49 times 1/2 times another 2. And even without a calculator, I should be able to do this. Now you might have a little trouble with the radicals, but 625 minus 49 is 576. What's the square root of 576? 24. Both places. And then right here you can see, well, that 2 is going to cancel with that 2. This 2 is going to cancel with that 2, but it is going to leave me a negative 1 up there. And I end up with a negative 7 times 7. So right here, a negative 49 over a 24. And then over here, that 2 cancels with that 2, plus a 24. And then you'd have to find a common denominator here, right? Yes, no? So, or write that as an improper fraction. I guess you could call that negative 2 and 1/24. But anyway, finding a common denominator here gives me 576 over 24, which gives me what, 527, maybe, over 24. And then what would my units be for my dA dt? What's area? Feet squared over seconds. So feet squared per second. And let me check the math. I have a decimal, which you on a problem like this more than likely would have a calculator anyway. But let's see if it ends up being 21.958. Good. So we did the math right. But you can probably bank on problems like this having a calculator for it. Then you just type it all in and write a decimal out to 3 decimal places. Not too bad?
Not too bad.
All right, what you got? 10 minutes? Let's look at C. All right, C says, find the rate at which the angle between the ladder and the wall of the house is changing. The angle between the what? Ladder and the wall. Every year I have somebody who calculates that angle. I mean, that's not a wall. Okay, this is the low. So I'm looking for that theta. Now, how would you like to find that angle? There's all kinds of trig functions. Anybody? Sine? Tell me why.
Because you have both the opposite and the hypotenuse already.
I think sine's a great idea. And here's why I don't think tangent's a great idea. If I were to right here say tangent of theta equals x over y, right? Which is true based on that theta, opposite over hypotenuse. When you take a derivative, you're going to end up with what three things in there? A d theta dt, a dx dt, and a dy dt. The only thing I know is what? That, right? That's all I know. Was that right? Dx dt was 2. Yeah. And they want to know the rate at which the angle is changing. They're looking for d theta dt when, again, x is 7. Now, like I mentioned before, we do know dy dt from problem 1. But most of the time, we're not going to get these kinds of problems. This doesn't happen anymore on an AP test. This was an old AP question. I might have changed some numbers, so I didn't have to give credit or something. But I don't like that because there's too many variables. But sine's great because this is a locked-in variable. So if I say sine of theta equals opposite over hypotenuse, and I know you're used to seeing for sine y over hypotenuse, but that's when the angle's down here, right? So sine of theta is x over 25. The great thing now is, if I take the derivative, I get the theta in there, the d theta dt and the dx dt, which I know. Are y'all seeing it? Okay, now, here's how you would do it like this. You would have to say, all right, what's the derivative of sine? Cosine of theta times d theta dt. Now, here's why I don't love this. I don't hate it, but I don't love it because I now have to find the cosine of the angle. And I can find the cosine of the angle when x is 7 and y is 24. It's not that big of a deal, but for you guys, it's one thing that tends to get you stumped. But we'll finish that up in a second. Now, what's the derivative of 1/25th x?
1/25
Times dx dt. So, for me now, to solve this, I would have to have a calculator and say, what is the cosine of this angle? And we know that the cosine of that angle, even though I don't know the angle, is what? When x is 7 is what? Adjacent over hypotenuse. Are y'all with me? So the cosine of the angle is 24/25. So actually I didn't have to find the angle in that case. I just found the cosine of it. I'm looking for d theta dt, so I'll leave that in there. And what is dx dt? 2. So all I have to do to solve this is to what? To solve for that? Multiply by a reciprocal. That all cancels there. And I get d theta dt equals, anything cancel? A couple of 25s, and I get 2 over 24, which is 1/12. And what would the units be? Very nice, because we don't do degrees, right? So radians per second. Now this is one option. If you went, oh, that's no big deal. The thing I notice the most about the mistakes is people get to cosine theta and they're like, I don't know that angle. Well, I didn't have to know the angle, did I? Right? But the second mistake I see is they forget to write d theta dt. And they plug everything in and they're like, what the heck happened? Now, where's the variable I'm solving for? For some reason, people forget this d theta dt way more than they forget things like dx dt. Now, here's an alternative for this. If sine of theta is this, then isn't theta equal inverse sine of that? And who remembers their inverse sine equation? For the derivative. Now, if you don't, then you're not going to be able to do it this way, but let me just show you. And sometimes this way is so great. It's not overly great in this case, but sometimes it's really great. So check it out. What's the derivative of theta? And the great part about this is I don't have to find the angle or the cosine of the angle or any extra step like that. Okay? And then what's the derivative of an inverse sine? Again, I'm ddt'ing both sides. What's the rule? It's the derivative of that, which is what? That goes on the top. 1/25 dx dt over what? The square root of 1 minus that squared. So it is very straightforward on this particular example. So all I have to do is go 1/25. The dx dt was a 2. And on the bottom, the square root of 1 minus 7/25 quantity squared. I mean, I can show you what to do if it's not. It's not that as bad as it looks, but probably would be, yeah. So in this case, if you really think about the math, I'm going to have to, if you were without a calculator, you would have 49 over 625, right? And I'm going to subtract that from 1, which is 625 over 625. And when I subtract them, I get what? 576 over 625? With this 2/25 on top. But again, if it was a calculator problem, it'd be pretty simple. And all you end up with is 2/25 on the top and 24/25 on the bottom. 25s cancel, 1/12. And again, radians per second. So if it was a calculator problem, man, done. And I just didn't have to do as much. Over here, I have to think, okay, I got this. Whoa, what about this? Oh yeah, cosine of that is this over this. It's just one more step. You don't have to worry about doing a d theta. It's pretty obvious here the derivative of theta is d theta dt. It's less likely to forget that kind of stuff. Anyway, are y'all with me? Now this is just one kind of problem. I'm not going to have time to get to the cone problem, but I have keys, all that stuff on Schoology. Please, for your sake, do these homework at the very minimum. Look at them and see if you can follow through my processes. And maybe at the very minimum, see if you can write down the stuff that they're giving you. Because all of that stuff's important to learning this. This is not a wing it section. All right? All right? Hey, has everybody gotten in my AP classroom? Is there anybody who hasn't? I had 4 people Friday. And I sent y'all a text. If there was anybody in here, I don't know.
Oh, what?
I don't remember.
I didn't get a text.
They're not going to order your test. If you don't, if you're not in, you might want to go back and double check, make sure you are. Here. Here.
You don't register for the AP test, you don't have to take it. They also get
Hey, you know what? I feel like it's something like
So,
Morning, Coach. So I heard you talk with Nathan about Moe's, and you said it's not the best restaurant of all time.
it is not.
It is. Moe's